Welcome to Math Day. I'm Chris Rhees, working here with Brenen Olsen. We are going to go over the Henderson-Hasselbalch equation. Whenever you are in a problem and you see pH, pKa, weak acid, or conjugate base, you're going to use this equation. The equation is pH equals pKa plus log of the concentration of the conjugate base divided by the concentration of the weak acid. The next thing you'll want to do is write down all of your variables. Alright, you'll notice that there's a fifth variable that is not in the equation, but it is associated with the problem. This is the total concentration of the buffer. And the equation that we are going to use for this is the concentration of the conjugate base plus the concentration of the weak acid equals the concentration of the total buffer. Alright, let's do a problem. It asks us to calculate the pH of a solution that is 0.06 molar acetic acid and 0.04 molar acetate with a pKa of 4.76. The first thing that we notice is that it is a Henderson-Hasselbalch equation, and we will want to write that down and our variables. Alright, now we need to find out which numbers go where. pH is what we're solving for, so we can just put an X there. pKa is given in the end of the problem. It's 4.76. Now these next two are a lot harder to find usually, so we're going to talk about how to discern which one is which. Alright, there's two ways to do this. The easiest way is first by the name. Acetic acid is going to be our acid, and acetate's going to be the conjugate base. But it's not always that easy. The other way you can do this is by looking at the chemical formula. If you're not given it, you can usually look it up online. But in this case, acetic acid has a chemical formula of CH3CO2H, and acetate has a chemical formula of CH3CO2-. You'll notice that acetic acid has an extra proton compared to acetate, and that's where we're going to look to find out which one goes where. The one with the proton is going to go in the box that has an extra proton on it, the acid. The lesser charge will be the conjugate base. Sometimes even looking at these formulas aren't going to be as easy, just as if we look at the formula for ammonia and ammonium. We'll notice here that ammonium has an extra proton and a higher charge. So the ammonia, the conjugate base, and ammonium will be our weak acid. Now let's go back to our problem and input our variables and solve this guy. So as we decided, our conjugate base is going to be acetate, so it's 0.04 molar, and our weak acid is going to be acetic acid, 0.06 molar. Now our total buffer solution is these two added together, which gives us 0.1 molar. So let's put these numbers into our equation and solve for pH. X equals 4.76 plus log of 0.04 divided by 0.06. So X equals 4.76 plus log of 0.666 continuous gives us X equals 4.76 plus a negative 0.176. X equals 4.584. And this is our final pH. Alright, now we'll do a little conceptual check on this number. If our pH that we got was the exact same as our pKa, that would mean that our concentrations were equal. But if we look back at our problem, notice that we have more acid. Therefore, we'd expect that the pH should be lower than your pKa. Remember, acids lower pH. The next part asks us if we need to add acid or base in order to get our pH to a 4.8. As determined before, our pH dropped by adding acid. In this case, we want it to go up, so we are going to add a base. Now that was the easy part. This is going to be the tougher question. It asks how much of a 1 molar titrating agent would you need to add to a 500 milliliter sample of the acetate buffer system to change the pH to 4.8. So if our buffer system is sitting at 4.58 and we need to get it to 4.8, then what can we change to get there? We can't change the pKa because that's a constant, so we need to change the concentration ratio. Furthermore, we need to realize that the conjugate acid and the weak base are linked together. What we mean by linked is that if we raise one of them, the other is going to have to drop. In this problem, we either need to find the change in HA or the change in A minus. In order to solve it, we are going to use the change in HA. In order to get that, we need a final and an initial concentration. Our initial concentration of HA was 0.06 molar from the previous problem, and our final concentration is what we'll be solving for. Alright, once again, let's write down our variables. Our pH that is desired is 4.8. pKa equals 4.76. Our concentration of A minus is unknown. Our concentration of HA is unknown as well. Our concentration of the total buffer is known from the last problem. It's 0.1 molar. As you can see here, we have two variables, which means that we need two different equations to solve for it. Our first equation is the Henderson-Hasselbalch equation. Our second equation was the equation that we used to solve for the total concentration of the buffer, which was A minus plus HA. Now, as we said before, we want to solve for HA in the end. So for now, we are going to solve for A minus in order for us to only have HA in the equation. We can now plug in our numbers and then plug in the whole equation here into the Hasselbalch equation. So let's scroll down and do that on the next page. So with all of our variables written out, we can now plug them into the equation and then solve for x. The first step is to subtract 4.76 over. You end up with 0.04 equals log of 0.1 molar minus x over x. The next step will be to get rid of log. In order to do that, we raise each side to the 10, and that gets rid of log. 10 raised to the 0.04 is 1.096, and this equals 0.1 molar minus x over x. We will multiply both sides by x in order to get rid of this one over here. We end up with 1.096x equals 0.1 minus x. Then add x to both sides, and we have 2.096x equals 0.1. If we then divide both sides by 2.096, we get x. And x equals 0.0477. Now, if you remember, the x was our final concentration of HA. So to get our change in HA, we had final minus initial. So we have 0.0477 minus 0.06, and that equals negative 0.0123. And again, this is the change in HA concentration. Now that we've solved for our change in HA, we can use that to solve for the original question, which asks, how much 1 molar titrating agent do we need to add to 500 milliliters of our acetate buffer in order to change the pH to 4.8? We can now use our change in weak acid concentration to solve for the volume of titrant we need. To do this, we'll first write down our change in HA, which is 0.0123 in molarity, which can also be written as moles over liters. We will then convert this into our titrating agent, NaOH. Now remember that for every mole of HA, we have 1 mole of NaOH. Alright, this cancels out our moles of HA. Now we need to take into account our volume of the buffer system, which is 0.5 liters.
Here you go.
The last thing we need to take into account for is the molarity of the titrating agent. That was 1 mole per liter of NaOH. So if we cross out our moles, this leaves us with 0.006 liters of NaOH. And of course we can write that out as 6 milliliters NaOH, which is our titrant. There is a much easier way to write this entire equation out, and I'll give you an abbreviated version of that right now. This equation is a shortcut, getting rid of the middle step, leaving us with change in HA times volume buffer divided by the concentration of the titrant, and that equals volume of titrant needed.
It's such a good feeling to know you're alive. It's such a happy feeling. You're growing inside, and when you wake up ready to say, I think I'll make a snappy new day. It's such a good feeling, a very good feeling, the feeling you know that we're friends. I like being with you. I'll be back next time. Bye-bye.